This video is going to wrap up our unit on logarithmic functions. It's going to cover our learning target number 3. I can graph logarithmic functions. It's important to understand as we move forward into graphing logs, as we compare them to graphing exponential functions, that we realize that exponentials and logarithms are inverses of each other. And when we create inverses, as we've done in all of our function units, we always start by switching the x and the y, and then resolving the problem for y. Let's try this process for logs. I have a function y equals 2 to the x power. I'm going to create an inverse of this function. So let's start by switching around the x and the y. I get x equals 2 to the y power. And the way that we solve this problem back into y would be changing it into log form. The y, which is the exponent, comes down and is on the other side of the equal sign. The log has the base 2, and it is of x now. So y equals 2 to the x power is the inverse of y equals log base 2 of x. Let's make a table of some values for each of these to compare what happens. Let's start with a good range. Let's try -2, -1, 0, 1, 2, 3, and 4. -2 is going to get plugged into the x, which is the exponent for the base 2. 2 to the power of -2 is 1/4. 2 to the -1 power is 1/2. 2 to the 0 power is 1. 2 to the 1 power is 2. 2 to the second power, 4, 8, 16. Let's try evaluating our log base 2 of x. When I plug in a -2 into our log, I get an error. It is impossible to do a log of a negative number. When I plug in -1, I also get an error. When I plug in 0, I also get an error. When I plug in 1, I get 0. When I plug in 2, I get 1. When I plug in 3, I get approximately 1.58. When I plug in 4, I get 2. There are values that I cannot plug into logs that I'll get errors for. -2, -1, and 0 don't work for this log. Also, there are some spots where you can easily see that the x and y are switched, which is what an inverse means, such as 0, 1, and 1, 0, 1, 2, and 2, 1, and 2, 4, and 4, 2. So the x and y values are switched around. Let's graph each of these set of points and see what the graphs of the exponential 2 to the x power and the logarithmic log base 2 of x look like and compared to each other. -2, 0.25, -1, 1/2, 1, 0, 1, 2, 2, 4, 3, 8, and so on. Now let's plot our points for the log. Not going to plot anything for -2, -1, or 0. I'm going to start at 1, 0. Then I'm going to go to 2, 1. Then I'm going to go to 3, 1.58. And then I'm going to go to 4, 2. If I had plugged in 8, I would have gotten 3. I can very easily see the curve of the exponential function, but what does this log look like? Here they are drawn out. You see they both have a similar curve, but one thing to understand is the way that this log curves down and looks like it's going to ride the y-axis, but it will never actually touch it. And the exponential function, like we already know, also looks like it touches the x-axis but doesn't actually touch it. Let's graph one of these logs from scratch. I'm going to start off by making a table of values. Remember, I cannot plug in negatives or zeros into this log because it is just log base 4 of x. It's just of x. I'm going to plug in some other x values that I know are going to output whole numbers, such as if I plug in 1, it's going to output 0. If I plug in 4, it's going to output 1. If I plug in 16, it's going to output 2. I'm not going to bother with the numbers in between because they don't give me whole numbers and don't plot very easily on our graph. So let's plot the ones I know. I have 1, 0, 4, 1, and 16, 2. I end up with a curve that looks like this. One new important piece of graphing that we're learning now is the idea that a graph can get really close to a line but never touch it. These lines have a name. They are called asymptotes. Lines that graphs get close to but don't actually ever touch. In this graph, the asymptote is a x value of 0. Because the graph will never ever get to x equals 0, which is indicated on our table as well. Also, it's important to explore the ideas of domain and range. In this example, there are x's that work and there are x's that don't. All x's that are bigger than 0 work, but not the x's that are 0 or less. So x is greater than 0. Our range is our y values. These y's on our table will go up and down forever. So the y's are all real numbers. Let's try another example. Y equals log of base 0.2 of x. Let's make a table. Again, remember, plugging in values such as negatives and zeros into this log are not going to output any values. They are going to give me errors. So I'm not going to bother plugging them in. Values that I do get outputs for are plugging in 1, I get 0. 2 is negative 0.4. 3, negative 0.6. 4, negative 0.8, and 5 is negative 1. So let's start to plot these. 1, 0 is here, 2, negative 4, 3, negative 0.8, 4, negative 0.8, and 5, 1. I see that this curve looks like this. Where is the asymptote? Again, it's sitting right along the y-axis, which crosses the x-axis at x equals 0. Domain, one more time, is all the x's to the right of 0, so x's that are bigger than 0. And our range, since the graph goes up and down forever, is all real numbers. This is our last example. In this example, I'm going to create a table of values. Now in this situation, I again cannot plug in negative 1 because negative 1 minus 1 is negative 2. That would give me an error because I'm doing a log to negative 2. If I plug in 0, 0 minus 1 is negative 1, still can't do it. And when I plug in 1, 1 minus 1 is 0, I can't do logs of zeros. So I would start by plugging in 2 and working my way up. 2, 3, 4, 5, 6, 7, on up. For 2, I output 0. For 3, I output 0.6. When I plug in 4, I output 1. 5 is 1.2. 6, 1.4. And 7, 1.6. It wouldn't be until I plug in 10 that I output 2. So let's graph these points. 2, 0, 3.6, 4, 1, 5, 1.2, 6, 1.4, 7, 1.6, and 10 outputs 2. This graph's asymptote is at 1, mostly because, as you look here, 1 is the last number that I cannot plug in. So that is where the asymptote is going to be. That is the limit that the graph has. It is never going to go past that point of x equals 1. Also, there's a little bit of a change to our domain and our range. Our domain in this problem now is x is only bigger than 1, and our range in this problem is still all real numbers. Don't forget to answer your questions after your video. If you have questions, write them down. We'll explore and review when we come into class. Don't forget to hit the submit button, otherwise I'm not going to have record of you participating in the notes.